tough. As you can hear, I'm not doing fantastic today, so I'm going to try to be loud, but my voice is a little bit impaired. Do you guys have, yeah, Mia? Which one?
6. 3.7.
3.7, number 6. Okay. Okay. This is what I want. All right. So it says the graphs of position functions of two particles are shown where t is measured in seconds. When is each particle speeding up? When is it slowing down? And explain. Okay. So speeding up, what am I looking for here? And so this would have related to, let's see. We did yesterday. So it would have been similar to this question here, right? So the question is, when can I tell if the acceleration is positive and negative by looking at the position graph? What is that going to look like? Everybody agree that if we know graphically what to look for on the position graph to indicate acceleration increasing or decreasing, then we could answer this question effectively. You guys cool with that? Well, we haven't talked about how to find that on, like what that looks like.
Okay.
Right, so we need to think that through first.
Okay. So we don't need to find, like, we don't need to look for velocity.
We do need to look at velocity also, but that we can tell by just looking at the slope.
Okay.
Right, as you suggested, which is correct. We do need to look at that piece, but that alone is not enough. So velocity, or the acceleration is positive when the slope of the velocity is increasing, right? Or when the slope of the velocity is positive, I should say. What is that going to look like in a position function? So if my position function is, let's say it does this. So I have positive slope throughout, right? Is it speeding up the whole time? Clearly not, because it basically comes to a rest here. Everybody agree with that? So here is the dealio. So if I look at this part where it's from the rest and then starts moving in, clearly it's going to be speeding up that whole stretch. If I look at this part coming into the rest, clearly it should be slowing down on that stretch. What do you notice about this green part of the graph? What do we call that? The way it's bending? This is called concave up, where it looks like a parabola, like it would hold water. And if I look at this section, this is called concave down, is it looks like it makes a roof where the water would spill off of it, right? So that's what I'm going to be looking for, is the places where the graph is increasing and concave up, or decreasing and concave down. Either one of those two would indicate that. Sophia?
At the top part of the concave up, when it's in a straight line, is that still speeding up?
Yeah.
Is that, okay.
Because if it stopped speeding up, it would just like, like turn into like a flat line or whatever. Or it wouldn't be curved anymore. Let me put it that way. Right? If it was just constant speeding up, it would just be.
But so just if it's like vertical, it'd be just speeding up really fast.
Yeah, real fast. Does that feel okay as to what we're looking for now? Okay. So speeding up, we're looking for positive slope plus concave up, or we're looking for negative slope plus concave down. So if I look here, that's a speeding up section, right? And somewhere probably in the middle-ish, it stops speeding up. So it looks like from 1 to 2, that's definitely speeding up, right? And then I would say again from like, what is that, 3 to the rest of it, looks like I'm speeding up. I would suppose that in the other two sections I'd be slowing down. So here for speeding down, we'd positive slope plus concave down, or negative slope and concave up. So it looks like here we're speeding up probably until we get to 1. And then we slow down for a minute, right? Because we're negative, but we're concave down. Oh, wait a minute, hold on. Negative slope, concave down, okay. That's negative slope and concave, I'm sorry. Hold on. Negative slope and concave up. Sorry. So we start off slowing down. And then we speed up. And we slow down again. And then we speed back up again. Does that feel okay, Mia?
Yeah, why is it like
we're negative slope and concave. Oh, negative slope and concave down, right? It is a little curvy downward, right? You got to pay attention, for sure. But that's the gist of it. I'm not doing any calculation, right? I'm just looking at a picture, and those are the two things I'm looking at. I'm looking at slope and concavity, and that tells me everything. Sure. That's a good question, because we did this, but we didn't do it by just looking at the picture, right? And we'll look at this some more in chapter 4. These ideas come back in chapter 4 in a big way when we start looking for extrema and being able to figure out what type of extrema we have without actually evaluating anything. Anybody else?
So,
oh yeah, go ahead.
will our answer just be us highlighting the graph if you put like points 0 to 1?
Yeah, so you would say like here speeding up, we'd say for like t on 1 to 2 and then 3 to positive infinity or something is how I would write that for the speed up. I just write them as intervals, but you could describe it in words. That's not wrong. You know what I mean? Sophia.
31 from 3.6.
Sure. All right. When I look at 31, it's asking to evaluate the first derivative when x equals 1. To do that, I'm just going to start by taking the derivative. If I look at my function f of x, this is a quotient rule situation. So f prime of x is going to equal the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over denominator squared. And I could simplify this, but I don't care to, because all I'm going to be doing is plugging 1 in immediately. So like, why bother, right? So I have 1 squared times 1 over 1 minus natural log of 1 times 2 times 1 all over 1 squared squared. So that's just going to be 1, natural log of 1 is? That's one you should know in your head.
This is why I didn't think it's long.
0, right? Anything to the 0 power is 1.
Yeah, I know. It's so good.
So that just comes out to be 1.
Oh, okay. Thanks.
Cool?
Yeah.
Yeah, no problem.
How do we discover the natural log of things? Like, how do we know that it's 0?
So the reason what we have here is I'm just kind of using the definition of a logarithm.
Mm-hmm.
So it's saying like, so if I'm doing this, if I have natural log of 1 equals y, that tells me e to the y should equal 1. What does y have to be? 0, right? Anything to the 0 power is 1.
Oh, yeah.
Right? That's how he's doing that in my head.
So then what if it was like the natural log of 5?
Not something I could do in my head. It's going to be a cuckoo decimal. Yeah. You know, something around 2 would be what my expectation, but because e is 2.7 or something, and 2.7 squared is going to be somewhere between 4 and 9. So 5's in there, probably a little bit closer to 4 than it is to 9. You know?
That's what I was thinking.
But like, doing any better than that is not something I could do in my head. Others, happy to do some more if we got some more. The 3/6 stuff should have been pretty okay, right? Very similar to things that we just got done testing on, so you should have felt pretty comfortable doing that. The 3/7 stuff shouldn't have been too hard, the stuff you've gotten to it, but that's assuming you've gotten to it, which is, you know, you had a lot to get through to get to that even in the first day, so. Yeah, Taylor.
Can you do 19 from 3.6?
19?
It's just one of the
Sure.
ones with the e to the negative x. I don't know what to do with that.
Sure. No problem. All right, so here it's asking us to find the first derivative. So when I do that, this is clearly a chain rule situation, right? Could I make this any easier by doing some algebra first?
Yes.
Yes. What can I do to make this easier by doing some algebra before we start?
We like take out the e.
Yeah, factor out the e to the negative x. Very good. Now, why is that to our advantage?
But you don't have to use the negative x.
Because now we can turn this into a product property. So if I use the product property for logs, I can rewrite that as the natural log of e to the x plus the natural log of 1 plus x. Right? Log of a times b is equal to log of a plus log of b. That's all I'm doing there. And this is lovely, because what is the natural log of e to the negative x? Just negative x.
So if it was like e to the fifth, it would be 5.
Correct. 100% correct. Tate's doing so far so good.
Yeah.
And now, look how much easier this is. Right? If I do the derivative of negative x is just negative 1. Derivative of log of 1 over x, well, that's a chain rule, so it's 1 over the inside times the derivative of the inside. So just negative x plus 1 over 1 plus x. You could make a common denominator there, I suppose, if you wanted to, but I probably wouldn't bother with it. How's that feel? Right? Look at what we avoided, though, by doing that algebra. Would have had a chain rule when we'd had to derive both, or do the derivative of each of those, and then this would have been a product rule. By doing a little bit of algebra in the beginning, got rid of a lot of kind of a tedious calculus by looking at that going, oh, I can rewrite this in a nice way to get out of a lot of algebra, or get out of a lot of calculus. And look at the answer I got at the end. Like almost no simplifying to do with that. Had I done this without doing the algebraic simplification in the beginning, the answer you're going to get at the end is going to be a monster. So particularly on like a show question where you have to get like a specific answer, that's going to be exceptionally helpful to get to the fully simplified answer first by doing some algebraic simplification first so that the calculus is easy, and then your answer you get is neater, right? Mackenzie. Yeah. Taylor, you happy there though? I didn't really address with the e to the negative x because we didn't actually have to do the calculus there.
But can I use what you did, like, anytime?
Yeah.
Then yeah.
Yeah, absolutely. You should, in general, you should always be looking first things first. Like, is there some sneaky algebra that I can do to take this crummy calculus problem and make it a much easier calculus problem? That's always a great first step. All right. 21, same deal. So I noticed that, again, I'm going to look, is there any sneaky algebra stuff I can do to make this a little bit nicer? Okay, so the square root of x we can turn into x to the 1/2. And then I can use my power property for logarithms. To rewrite it like that. So the 2 and the 1/2 just kind of cancel out. And now I'm left with just a product property with no chain rule. Right? Got rid of the chain rule, which is nice. One less thing to have to worry about. So x times the derivative of log base 10 of x is going to be 1 over x times the natural log of 10. And then plus log base 10 of x times the derivative of x, which is just 1. That's it. You know, we can clean this up a little bit and those will cancel out. So I have 1 over the natural log of 10 plus the common log of x. That's probably where I would leave it. Which again, simplifying wise, that was not too bad, right?
You didn't like automatically tell you were moving x, and then you have to cancel out the x.
The derivative of x.
Like, you found the derivative of the log of 10.
Yeah, I just did the derivative of this.
Right. But you didn't, right? So what about the x? I know it's just 1.
Yep, that's what I did here.
Oh, product.
Product rule.
Right, okay.
Because you have two things multiplied together. Two different x's, right?
Okay.
I see two different x's. There's going to be some kind of product or quotient going on. The x's here were multiplied, so it's a product. Is that cool? Okay, follow up on this one before I take next questions. Okay, I just saw 3 hands come up, so I'm just checking before I move forward. Serge.
Oh, my contacts all screw up. What happened?
Yeah, absolutely. That's something you could just like wave at me on the way out. That's okay. You guys are trustworthy enough that that's, yeah. So,
Can you do 13, please?
same section?
Yeah.
Sure.
I forget what we complicated it, but.
Well, there is certainly some stuff to do to make this not as bad as it has to be. All right. So I look at this, and this looks like a nightmare right away, right? You have 3 chains and a quotient. But is there some algebraic stuff I can do to make this easier? Yeah, so I would start by doing a quotient property. So that's going to give me log of the numerator minus log of the denominator.
You mean LA?
Yeah,
Oh, yeah.
natural log is still just a log. So I'm when I say this, I'm just going to say log in general.
Right. So log has properties and like the calculus has rules.
Yeah. So again, there's 3 properties of logs: the product, quotient, and power property. And then there's derivative rules for how you do the derivatives. So we're still doing algebra right now. And then I notice in each of those logs that I've created, there's a power property.
So how do you know that you want to do that instead of the power rule?
Well, because when I'm looking at this right now, this piece has 2 chains in it. When I look at this, I have 1 chain. Would I rather do that little simple algebra thing and deal with 1 chain rule versus 2 linked chain rules? Yeah, I would. Now, could you have done it just right from the get-go, done calculus here? Sure. Is the answer you get kind of a nightmare? Yeah. Yeah, it's going to get real ugly. Now, though, if we take what we have and now we do the calculus, this should be not too bad. So I have 5 times, and then this chain rule is going to be 1 over the inside times the derivative of the inside. And then another chain rule, 1 over the inside times the derivative of the inside. And if I wanted to clean this up a little bit, I could write it like that, but that's probably where I would stop. I wouldn't muck around with making common denominators or anything.
Could you like
What's up?
take
Oh, yeah, let's cancel the 2's. Thank you. For sure. In fact, let's do that back here. Thanks, Elvis. What's up? Same thing? Great. I love that you guys are like on the ball paying attention. Taylor.
If you're taking the derivative, can you take the derivative of a natural log just like a number?
It's 0 because it's a constant.
It's 0.
Right? The natural log of a number is just a number. That's a constant.
Okay.
So like the natural log of 6 is 0. Or the derivative of the natural log of 6 is 0. Because you're just taking the derivative constant. You know? Is that cool with everybody? Mackenzie? Sure. This one's a little bit different because we're asking for the first and the second derivative. So the directions on this one change a little bit. All right, let's take a look at this one. Any sneaky algebra I can do in the beginning to make my life easier here? So the answer to this is no. Why can't I do any separating here? Because they're being added and not multiplied. If it was x times the square root of 1 plus x squared, product rule or product property of logs, absolutely. But the sum of logs doesn't help you any. Everybody, is that okay? So there's not any obvious algebraic shortcut that I could do here. So let's just start by doing the first derivative. So I'm looking at a chain rule for the natural log. So that's just going to be 1 over the insides times the derivative of the inside. So the derivative of x is 1. And the derivative of the square root of 1 plus x squared is also a chain rule. So the derivative of the outside is going to be 1/2 the inside to the negative 1/2, and then times the derivative of that inside.
So that's because if you got rid of the square root and you did 1 plus x squared, it would be to the 1/2 power.
Yes.
And then bring it down and then do subtract.
Yes, 100%. That's exactly what we're thinking of. Mm-hmm.
Could we have done that in the beginning and like put that under the 1 over x plus?
No, because of the addition. So the power proper needs to have the entire thing inside the logarithm to the power, which I don't have because I have the plus sign.
Right.
Yeah. So let's see. Those guys can reduce. And then this will be oops, and I have an X on that. which is looking pretty nasty here. Can we make this any nicer? Well, not exactly because of the addition,
Oh,
right?
what? No.
So because of that addition symbol here, I can't just stick it onto the bottom.
Even if it's a negative one.
So what it would become is this piece up here, I could write as but now I have like a complex fraction when I multiply that in over 1 to this piece. You see the problem? That addition sign really kind of gets in the way. What would be okay to do is you could multiply the top and bottom by like this. So that would like distribute through, but I don't think you really get anything better. You could do that, but I don't know that that's really any better than what we had before. Do you? So just like extra work for, I don't really see any good reason. I don't know what the answer in the back of the book gave, Mackenzie. Oh, they did some kind of clever simplifying then. Let's take a look. Or I made some mistake, or maybe the answer in the back of the book is wrong. Any of those things are entirely possible. Let me look at the worked out solutions here and see if they did something sneaky that I wasn't anticipating them doing here. Okay, we're at the same thing I had there. They did that. Okay. Ah, that's interesting. Okay. All right, so watch this. Watch this. I'm going to get rid of... All right. Okay. So let's imagine that we did think about it this way.
I'm just confused why there's no like square root on it if it's a negative 1/2.
I put the 1/2 in the denominator, right? That's the same thing as a square root,
Oh, okay.
right?
You're thinking about it, the one that's circled.
Yeah,
Okay.
yeah. Let's make a common denominator with that. What would that common denominator be? Be 1 plus x squared to the 1/2. That's correct. Ugh. Guys, ugh.
Yeah, I agree.
Okay. So far, so good. I rewrote them with square roots on them than the 1/2 because the next step, it's going to be advantageous that you see the square root there.
Where's the other plus x plus x? So you want that at the
So I have this thing becomes square root 1 plus x squared over square root 1 plus x squared, right? Because it's just 1.
Right.
So that's this plus x, and then that's my common denominator, right? Because we're multiplying those two together. We don't need a common denominator to multiply two things. I just need a common denominator to add the stuff that was circled in yellow. Cool? Okay. Anybody see the simplifying that can happen here? So if I do that, I have square root 1 plus x squared plus x over x plus square root 1 plus x squared times square root 1 plus x squared. And that's way better. That now looks like something I'd like to take the second derivative of versus what we had before where it's like, do I really need to do this? This feels bad. I'm glad we double checked the answer. That would not have been my first thought to add those fractions there, but I see now why that was advantageous, and I see now that if I have like a fraction times the sum of two fractions, that to have any hope of reducing, I'd need to add the two fractions together. So I've just fraction times fraction so that there's a reducing possibility there. That's a good observation to make. Right, here I had fraction times the sum of two fractions. To have any hope of reducing, that sum of two fractions needs to be written as a single fraction, which I did there. And then there was some reducing potential that happened.
So this would be more like a show problem.
Yeah, screams of a show problem. Okay. And then Mackenzie, to do the second derivative, I would just think about this as that. So it's just a simple chain rule. Times the inside. So we got here negative x over square root 1 plus x squared cubed. That's a good one to ask about, Mackenzie. If you could get the first derivative simplified, the second derivative was cake, right? That wasn't bad. The hard part was simplifying that first derivative. But on a nested problem like that, like the simplifying step really helps, right? If you have to do multiple derivatives, like making sure that first derivative is well simplified can take a problem that was going to be really terrible and make it okay. That's not bad at all. All right. Can we do 3/8 here?
If you must.
We kind of need to. All right. So in 3/8, again, this is just like a section of story problems. So these are all about exponential growth and exponential decay. So it says that the only solutions of the differential equation dy dt equals ky are the exponential functions of the form y of t equals y of 0 times e to the kt. So what is this, what was this dy dt equals ky representing? The change in y over the change in time is a rate, right? The rate of change in y is ky, which would say it's linear, right? The change is constant, or is a like linear change. Everybody's okay with that? All right. So if you go back, we're going to go and look at some story problems, and these story problem examples we'll look at are going to sound very much like Algebra 2 kind of problems to a great extent. This is pretty close together, Mr. Kulik. All right. All right. So it says, use the fact that the world population was 2,560 million in 1950 and 3,040 million in 1960 to model the population of the world in the second half of the 20th century. Assume that the growth rate is proportional to the population size. What is the relative growth rate? And then use the model to estimate the world population in 1993 and predict the population in the year 2020. Okay? So I'm going to be using this equation. So I'm going to use P for population. So I'm going to say that 1950 is time 0. So this one would be time equal to 10. This one would be time equal to 43. And this one would be time equal to 70. So far, so everybody okay with that? So I'm going to say P of 0 is equal to 2,560 e to the kt. That's just using that our population was 2,560 million in 1950, which is time 0. Similarly, I guess this should really be P of t. So if I talk about P of 10 then, yup.
Did you hear that?
Yeah.
Do you have like super hearing?
No.
No, you were pretty loud.
It was very quiet in here.
Yeah. No, this is the way
my ears are clogged up.
something I better know.
So far, so good?
Yeah.
I have a question.
Oops. This was not supposed to be, that was supposed to be 10K. My apologies. Yes.
So in the original equation, it's like y t is equal to y parentheses 0.
So y of 0, in our case, we're doing is P of 0, right?
Was this the partner test we did last year? I don't think so, right?
Shoot, man, I don't even remember.
It was.
Okay. So, how do we solve for k?
Why are we still using the 25, 2006 for y? We wouldn't use,
Because that's y0,
okay.
right? That's a constant. So solving for k, Mia.
Is P of T the same as P of 0?
No, p of t is my y of t. That's the name of my function.
Okay.
Is that okay? So I'm just starting to write the original function, but I still need k, right? It says, what is the relative growth rate? That's what we're going to be finding. That's our k. Okay, to solve for k, I have this equation. What do I need to do? Divide both sides by 2,560, then what? Do the natural log of both sides, and then what? Divide by 10. Good. And then that's calculator time. So our relative growth rate is about 1.7% per how long? Year. Just years. Because our time was t, going up by 1t is 1 year, right? So that's that. So now if I want to estimate the population in 1993,
Wait, what? So why did we multiply it by 100? Why?
well, it says the relative growth rate, so I wanted to write as a percentage,
Okay.
right? So just a percentage. So when I plug that in, I get 5,360 million. And then we do the same thing for 2020, except we're plugging 70 in. When I type that into my calculator, Sophia?
To get the relative growth rate, does it matter if you do it between like 1950 and 1960 or 1950 and 1990? Would you would it all end up being?
Well, you don't have the population 1993.
You did. Like,
No, it wouldn't necessarily. I mean, if this is real data, no. So you're using the data you have from 1950, 1960 to extrapolate what the data in 1993 would be. Now, things could have happened between 1950 and 1993 that could have cratered the actual population growth. Like you could have had an actual like real life plague, or like a world war or something that really kind of hammered down the population growth in those intervening years. So you'd have, like there's a lot of reasons why that would get a different answer.
So then, do you just choose the two that are closest to each other?
Typically, you'll use the stuff that you're given.
Oh, so you'll only be given the population.
Yeah. 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 Now, looking at this, what's the question you should be asking? Where's the calculus? Because did we do any?
I'm not asking that question. I like the way we're doing it.
Where's the calculus?
The calculus was that I got to use this equation. That was where the calculus happened. Well, we gave you the model. We gave you the model, and you filled it in last year. The calculus explains why this model fits the situation. I'm not going to go like bananas in this because, quite frankly, we're a little behind where I'd like to be right now, and it's not that important for the AP exam, at least. So we're just going to go ahead and do a couple more examples and get out of this section. Okay? All right. Radioactive decay. So the half-life of radium-226 is 1,590 years. A sample of radium-226 has a mass of 100 milligrams. Find a formula for mass of the sample that remains after T years. Okay. Again, what's the calculus piece? So I'm going to use M for mass. What is our M0 in this case? Our mass at time 0? Right? That's the mass at time 0. But Mr. Kulik, where's the other data point or whatever that I need? It's right there. What is that telling us? That M of t should equal, or I'm sorry, not M of t, M of 5,900 and, or 5,000, 1,590 creepers should equal 50 milligrams, right? Is that okay? You guys see it? Now we're just going to solve for K. Yeah, to find the formula, we need the K. We found the M0 right away, but to find the K. So divide by 100, natural log of both sides, and divide by 1,590. Now I want to point out to you guys here that this is something you can just get a decimal from, right? Now that's a crummy decimal to hang on to, isn't it? What the textbook did when they wrote their answer, so they said, okay, 50 over 100 is just 1/2. I did the quotient property for logarithms to rewrite it like that. What's the log of 1? 0. So they went and wrote their k this way when they did this example. I think mostly because the number was quite small and the decimal is just going to be kind of a lot of zeros to keep track of. It's fine to use the decimal. Okay, I want to be clear, it's fine to use the decimal. So if you look at something in the answer key and you're like, where the heck did they get that from? It's probably the same thing as the decimal you have.
So they didn't find like the log of 2.
Yeah, they just, well, the decimal that comes out to be when we do this is like, so I have 3 zeros and then it's just going to be a lot of decimal, like digits to write down to keep track of. So they just wrote it like this to give the exact value, just fine. It's the same thing. It'll be good enough. So our final answer, or their final answer that they wrote, for part A was this. And then it says, find the mass after 1,000 years. Okay, so what am I doing there? Just plugging in 1,000. So that's about 65 milligrams. Again, if you want to see that on the calculator, 100 times e to the that number times 1,000. Rounded to the nearest milligram is 65. Everybody cool there? No big deal, right? And then the last question it asks us to do is find when. So we're asking to solve for t. We'd have 30 milligrams left. So again, just pure algebra, right? Divide by 100, take the natural log of both sides, and then multiply by the reciprocal of -2, natural log 2 divided by 1,590. I think I said an extra 2 in there somewhere. Actually, that's just a fat equals.
Wait, can you show? Wait. Can you show how you got your like
Divide both sides by 100. Took the natural log of both sides. And then multiplied by the reciprocal in the exponent. Right? So that comes out to be about 2,762 years. What do you guys think on this? This is not too bad, I hope, right?
Like he was so dead serious.
I have a question.
Yeah, go ahead, Vicky.
How did you know like it was 30?
Because it says, when will the mass be reduced to 30 milligrams? This feels like enough, right? Like this is just the same stuff we've done in Algebra 2 and in Trig last year, or it should be pre-calc. And I don't need you to do much from this section. I think I picked I picked 6 problems. That feels like plenty from here.
Seriously, yeah.
I see like 1, 2, 3, 6 problems. That's perfect.
Yeah.
That's I mean, that's
They're
actually
just gonna
doable.
be sitting in the big house and doing some math.
Okay.
So, I think that's doable.
All right. I do want to start 3-9 here. 3-9's a tough section.
Wait, was this 3-8?
Yeah. I recognize that 3-9 is typically a tough section. We're going to go through it slowly. I'm going to spend more than 15 minutes here today talking about it, but I just want to kind of get started on the idea, because from a technique standpoint, a calculus standpoint, it's nothing new.
Is 3-9 on the test?
Yeah.
Yeah.
When is that going to be?
We're doing up to 310. We're not doing 311. It's not on the AP exam. We're not doing it. So probably not next week because we have only 2 class days. So probably the week after, though. All right. So 3-9. The title for 3-9 is called Related Rates. So in this kind of section, we're going to be solving almost always for a derivative, the value of a derivative. The techniques we're going to be using to do this is going to be almost all the implicit differentiation techniques. So we're going to write an equation that has lots of variables in it, take the derivative, fill in the values that are given to us in the problem to find the missing piece. Everybody's okay with that? At the basic level, these problems should feel very comfortable. What gets tricky is, as they get more complex, the basic equation that you write, you're going to have to alter, because when you take the derivative, you're going to get quantities that you don't have values for if you don't. And we'll look at that we'll look at some examples of that tomorrow. Today we're going to stick with like 2 examples of the kind of the basicest situation. Okay? Example 1 says air is being pumped into a spherical balloon so that the volume increases at a rate of 100 centimeters per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeters? Okay. So first thing I'm going to do is identify the equation that I would be using that relates to this situation. We're talking about volume of what type of shape? Sphere. So the volume of a sphere is 4/3 pi r cubed. I'm unclear as to whether on the AP exam that would be provided in the story problem within the context of the story problem, or there you would be responsible for remembering these on your own. My suspicion is some of these basic volume ones that you probably would not be ill-suited to try to memorize a handful of these. Basic things like sphere, cylinder, cone would probably be a decent idea. Okay. After I've done that, I want to examine what quantities I'm given. So I'm told that the volume increases at a rate of 100 cubic centimeters per second. What is that number? Look at the unit. Look at the unit. That's a cubic centimeters is a measure of volume. And then the seconds is a measure of time.
Yes.
So what do we have here? A rate. We have dV dt. We're told that the volume is changing at a rate of 100 cubic centimeters per second. It then asks us, how fast is the radius of the balloon increasing? What is that quantity going to be? That's going to be dr dt. That's what we're going to be solving for. And then we're told that the diameter that we're interested in, actually let's say it this way, dr dt when the diameter is 50. That's probably the better way of writing that. Yes, we should.
Oh my gosh. Wow.
Very good. Why did we want to change that diameter into a radius? Look at my formula. Okay? Is everybody okay? Now it's time to take the derivative. What am I differentiating with respect to? T, time. How did you know that? Yeah. So we're doing ddt of both sides of this. Okay. The derivative with respect to time of v is going to be dv dt times 1. Right? When I differentiate with respect to a differential variable with respect to some other variable, I do the derivative using my rule, but I also get that differential term. Same thing over on the other side, right? Cool so far? Hopefully you noticed that you can do a little bit of light reducing there. And we're left with dv dt equals 4 pi r squared dr dt. So to get the dr dt by itself, we'll just divide both sides by 4 pi r squared. And now, if I want to evaluate this when the radius is 25, I'm just going to plug that in. That's the value for dv dt that was given to us in the problem, remember? That's okay. So when we do that, we get about 0.0127 watts. So the centimeters per second, right? Because the radius was measured in centimeters. So that means that when we're blowing this balloon up, where we're adding 100 cubic centimeters every second, that's the rate in which our pump is like filling this balloon. When the diameter got to 50, the radius was growing at a rate of 0.0127 centimeters per second. And so? Sure.
So d over dt times 4 over 3 minus 2.
Yeah.
And then you broke it down to 5 over 3 pi times
I have 4 over 3 pi.
yeah.
Yep, times the derivative of r cubed. So if I have like ddx of like a constant times my function, I just can pull the function out front, or pull the constant out and just do the derivative of the function. So that's what I did there, is I just pulled off the 4/3 pi and then just took the derivative of r cubed. Is that okay? And this is something that like is super duper basic, and I saw a lot of people not doing this on their test. If you haven't been doing that, like that is a super useful calculus rule. Like you can do that. You can just ignore the constants, pull them out, take the derivative of the variable parts. You know what I mean? All right, one more example to try to do, and then we'll call her good for today. All right. Go away. All right. It says a ladder rests along a vertical wall, or a 10-foot long ladder rests against a vertical wall. If the bottom of the ladder slides away from the wall at a rate of 1 foot per second, how fast is the top of the ladder sliding down the wall when the bottom of the ladder is 6 feet from the wall? So let's draw ourselves a little picture. So I'm going to call that distance from the wall to the bottom of the ladder x, and the distance from the top of the ladder to the bottom of the wall y. Everybody's cool with that? I used x for the horizontal and y for the vertical. It feels like that makes the most sense. So what formula is going to dictate this situation? Pythagorean theorem. Yep. Okay. Let's identify some of these quantities now. If the bottom of the ladder slides away from the wall at a rate of 1 foot per second, what is that quantity? Yeah, it says if the bottom of the ladder slides away from the wall at a rate of 1 foot per second, what is the 1 foot per second? What quantity is that? It's a rate describing which variable? X or y? X. So that is dx dt equals 1. And then it asks, how fast is the top of the ladder sliding down the wall? What is that going to be? That's what we're looking for. dy dt. And it says when the ladder is 6 feet from the wall, so when x is equal to 6. Everybody cool?
Yeah.
Okay, we do our calculus, 2x dx dt plus 2y dy dt equals 0. If I evaluate this when x is equal to 6, what's my problem here? Don't know what y is, but sure I do. How would I find y? Right? Just the Pythagorean theorem.
Wait, what? Oh.
So y squared is going to equal 64. So y will be 8. So I'm going to get 12 divided by, or negative 12 divided by 16. Or negative 0.75 feet per second. Can you guys, before next time, look at numbers 3 and 5 from this section? I don't care if you've started the other homework or where you're at in the other homework. At least try these two. So when we come back, we still have at least another day doing this section and looking at examples of things. But at least take a look at those 3 and 5. Should be very similar to the things we did here today.